Welcome to Lean Engineering, the basics. The following section will provide an introduction to the course and an overview of Lean practices before we delve further into Lean principles at later sections. For now, let's begin. So, what to expect on this course? This course will provide you with a foundational knowledge of Lean principles and practices, along with practical tools to apply in your work environments. The focus will be on improving efficiency, eliminating waste, enhancing collaboration, and fostering a culture of continuous improvement. Hopefully, you'll be able to go away and apply some of these principles to your organisation and make improvements. What is Lean Engineering? Lean Engineering enhances efficiency, innovation, and competitiveness in engineering and manufacturing operations by optimizing resource use and minimizing waste. This philosophy identifies and eliminates waste, including unnecessary transportation, overproduction, excessive processing, inventory management, and waiting times. Activities that add no value to the customer. Central to Lean Engineering is a focus on people and continuous improvement. It employs techniques like quality management, job organization, production flow optimization, supply chain management, and proactive maintenance to streamline operations and improve outcomes. The ultimate goal is to foster a culture of improvement based on communications, teamwork, and adaptability. Lean engineering challenges traditional methods, seeking agile, flexible, and economical approaches tailored to specific needs. By emphasizing value-driven processes and eliminating inefficiencies, it delivers measurable benefits while creating a mindset of innovation and efficiency across a whole organization. Let's take a look at the history of Lean, its timeline, and key influences. In the 1950s, the Toyota production system was developed, focused on eliminating waste, improving flow, and optimizing value delivery in manufacturing. This introduced concepts like just-in-time production and automation with a human touch. In the 1970s to 1980s, Lean philosophy grew within Western companies, and researchers began studying the Toyota system, with American engineers and business leaders visiting Toyota's facilities. Concepts were applied in industries beyond manufacturing, sparking interest in other domains, including production development. In the 1990s, the book The Machine That Changed the World was published by James Womack, Daniel Jones, and Daniel Ruse. This introduced the term Lean as a description to Toyota's methodology. It highlighted the potential for applying Lean practices in various fields. In 1996, Lean Thinking by Womack and Jones expanded the Lean philosophy to encompass the entire value stream of a product, from concept to delivery. This encouraged applying Lean principles in engineering design and development. Now, in the 21st century, Lean engineering emerges as industries embrace Lean principles, engineering teams began integrating Lean principles like value stream mapping, concurrent engineering, and set-based design into their workflow. Lean engineering became critical in sectors like automotive, autospace, software development, where efficiency and innovation are paramount. What are the key principles of Lean engineering? First off, value identification. Understanding what the customer values and focused efforts on delivering that value. Anything that doesn't contribute towards value can be considered waste. This matters as clearly identifying value ensures resources can be used effectively to meet customer expectations. Next, waste elimination. Identifying and eliminating all forms of waste. Lean recognizes 7 types of primary waste, which will be covered later in the course. Removing any waste reduces costs, increases efficiency, and improves customer satisfaction. Flow efficiency. This ensures a seamless flow of materials, information, and work across a production process. Bottlenecks and interruptions should be minimized. This matters as a smooth flow reduces delays, improves productivity, and enhances the ability to deliver products or services quickly. Continuous improvement, also known as Kaizen. This fosters a culture of regular incremental improvements in processes, products, and services. Everyone in the organization is encouraged to contribute towards ideas of improvement. This matters as small, consistent changes accumulate to significant improvements over time. Respect for people. Empower and involve employees at all levels, respecting their ideas, skills, and contributions. Teams work collaboratively to solve problems and improve systems. This matters as engaged and respected employees are more productive, innovative, and commit to organizational goals. Finally, systems thinking. This is a view the organization as an interconnected system rather than isolated departments. Understand how changes in one area can affect the whole system. This matters as a holistic approach prevents localized optimizations that might negatively impact other areas. Common practices in lean engineering. Concurrent engineering. This is where teams work on different phases of a project simultaneously rather than sequentially. For example, design, manufacturing, and testing teams collaborate early in the product development process. This reduces overall development time by overlapping tasks. It enhances collaboration and reduces rework by identifying design issues early on. It improves product integration since all aspects are considered from the outset, but this does require strong communication, effective tools for collaboration, and a well-defined process. Set-based design. Engineers explore multiple design solutions simultaneously instead of converging quickly on one option. Gradually, infeasible options are eliminated until the optimal solution is selected. This promotes innovation by encouraging diverse ideas, reduces risk by delaying critical decisions until more data is available, and it helps avoid costly late-stage changes by considering a wide range of possibilities up front. Value stream mapping. This is a visual tool used to map out and analyze the flow of materials, information, and processes required to deliver a product or service. This highlights bottlenecks and areas of waste. It facilitates prioritization of improvements and efforts and encourages team alignment towards a shared goal. Just-in-time development. Delivering work, products, or materials just in time to meet the next step's needs, avoiding excess inventory and unnecessary effort. This reduces storage and inventory costs. It also minimizes the risks of developing outdated or irrelevant designs. It keeps teams focused on immediate priorities, but requires precise planning and reliable communication across teams. Rapid prototyping and testing. Quickly creating and evaluating prototypes to test ideas and gather feedback iteratively. This accelerates the learning process by identifying flaws or areas for improvements early on. It reduces the risk of investment in unproven designs and supports continuous improvement through frequent iterations. Cross-functional teams. Teams composed of members from diverse disciplines working together on a project. This enhances communication and understanding of interdependencies. It encourages holistic problem solving by incorporating multiple perspectives. Pull systems. Work is initiated only when there is demand for the next step in the process, avoiding overproduction or premature task integration. This prevents overloading teams with unnecessary tasks, increases its focus on high priority deliverables, improves overall efficiency by aligning production with demand. Continuous improvement. An ongoing effort to refine process, tools, and workflows to improve efficiency and eliminate waste. This fosters a culture of innovation and adaptability. It encourages small incremental changes that accumulate to significant improvements. It engages all team members and problem-solving skills and enhances all processes. Standardized work practices. Documenting and adhering to best practices and standardized processes for repetitive tasks. This reduces variability and errors in engineering outputs. It facilitates knowledge sharing and training of new members of staff, and it supports scalability by providing a foundation of consistent quality. All these practices are often tailored to fit the specific needs and constraints of an organization or a project. It ensures that lean principles are effectively integrated into the engineering process. We've already mentioned them a few times, but the benefits of lean engineering. Reduce waste. Lean identifies and eliminates waste in various forms, such as overproduction, excess inventory, waiting times, and unnecessary movement. This leads to a more streamlined operation, resulting in lower costs and more efficient use of resources, contributing to improved profit margins. Improved quality. Lean emphasizes continuous improvement and the elimination of defects, focusing on delivering high quality products or services, resulting in fewer defects, lower rework costs, and improved customer satisfaction. Faster time to market. Lean methodologies, like concurrent engineering and pool systems, help reduce delays and ensure that tasks are completed only when necessary, resulting in products or services being delivered faster, enabling organizations to meet market demands more swiftly and gain a competitive edge. Lower costs. Lean focuses on optimizing resources, reducing waste, and improving flow efficiency, all of which help reduce operational and production costs, resulting in cost savings in areas like labor, material handling, and storage, making the business more cost competitive. Increased employee engagement. Lean involves employees in decision making and continuous improvement process, respecting their contributions and empowering them to identify solutions, resulting in higher employee morale, greater job satisfaction, and more motivated workforce that drives productivity. Enhanced flexibility. Lean practices encourage adaptability and flexible workflows, allowing organizations to quickly respond to changes in customer demands or market conditions. This results in greater agility, enabling the organization to pivot or adjust with minimal disruption. Better resource utilization. Lean focuses on optimizing the use of materials, time, and human resources, ensuring that every resource is put to its best use, resulting in maximized productivity and minimized waste, leading to overall resource efficiency. Improved customer satisfaction. By focusing on customer value and eliminating non-value added activities, Lean helps deliver products or services that meet or exceed customer expectations, resulting in higher customer loyalty, repeat business, and enhanced reputation within the market. Sustained long-term improvements. The Lean philosophy is built on continuous incremental improvements that are sustainable over time, resulting in ongoing operational enhancements that keep the organization ahead of its competitors. Better decision making. Lean emphasizes data-driven decision making, informed by accurate and timely information, often through the use of tools like value stream mapping and root cause analysis. This results in a smarter, more informed decision-making process that lead to better business outcomes. Hopefully you'll now see why Lean principles should be applied to all aspects of engineering, and how they can demonstrate an effective and efficient way to provide optimizations. For my core course, please visit Udemy in the link in the description.